Hi, class. Welcome back. It's Dr. Lindner. We are still on chemistry. I know it's a very, very long topic. So, we're going to be looking at chemical reactions in this next round. So, chemical reactions occur when new bonds are formed or when old bonds are broken. Okay, that's when chemical reactions occur. It's either new bonds are going to be formed or you got some old ones and we're going to break those bonds. When we look at chemical equations or chemical reactions, on one side, we have reactants. That's what you're starting with. And then on the other side, we got the products. That's what you're going to end up with. And the metabolism is the chemical reaction that's taking place. And here, there's some sort of metabolic activity that takes place in order to create those products. Now, energy is the capacity to do work, right? If you don't have energy, you can't go to work. Oh, I have no energy. I can't study. I can't go to work. We need energy in order to do that. And energy comes in different flavors, right? We have potential energy, kinetic energy, and chemical energy. Now, there's something called the law of conservation of energy, which states that energy can't be created and it can't be destroyed. It kind of always is, always was, and always will be. It just kind of gets converted from one form into another, right? Like a leaf on a tree that dies, it falls to the ground, and through metabolic activity with the rain, with the snow, it breaks down all of those elements in the leaf, drives it down into the soil, and now that energy gets recycled into the ground so that the soil is more nutritious to grow crops, right? Energy is just being transferred from one form to the other. So energy is the power to do the work. What's work? It's the change in mass or the change in distance. Or change in mass, if you change, let's say, a puddle of water that starts to dissolve in the air and become steam or a gas, that requires work. So if you're changing the mass or you're changing the structure of that, that all requires work, right? So going from like solid, like from ice to water, from water to gas to steam, that's all requires work. Now, the difference between kinetic energy and potential energy is the stored energy. It's like you have a battery that's sitting on your desk, but it's not plugged into any type of device. We know that the battery has got stored energy, right? It's got the potential to do something, but it's not doing anything yet. But when it's plugged in and it's doing something, now we have kinetic energy. Kinetic energy is actually energy in motion, right? Now, chemical energy is the potential energy that's stored in chemical bonds. And when you break a bond, you're releasing energy. Okay. When you make bonds, it takes energy, but when you break a bond, it's releasing energy. So cells perform work as they synthesize complex molecules into, out of, and within the cell. So your organelles, they're all working. And that work is going to take energy, right? The cells of skeletal muscle at rest have potential energy. And the potential energy is in the form of protein filaments. And the protein filaments are held together by covalent bonds. When those covalent bonds are broken, it releases kinetic energy. That's energy in motion, and now you can perform the work. When the energy is released, the cells can perform their function. When the muscle contracts, it's performing work. So what ended up happening was the potential energy, which was the stored energy, is converted into kinetic energy, energy in motion. And when that happens, heat is released. And that's why you perspire when you're exercising, right? As a result of the exercise, your body temperature feels warm. You're getting hot because those muscles contracting create energy, and energy releases heat. We perspire to cool us off. Now, types of chemical reactions, these are some of the biggies that we'll talk about. We have a synthesis reaction. The word synthesis means to synthesize, means to manufacture or to make. So synthesis is when we're building something up. Decomposition, and another word for synthesis, we can say anabolism. Anabolism is building up, whereas decomposition sounds like decompose is catabolism, which is to break down. So you have synthesis reactions, anabolism, which is building up, decomposition, which is breaking down, catabolic or catabolism. Exchange means that whatever you have on one side of the equation, let's say it's blank plus blank equals blank plus blank. It's just reorganizing whatever we have, whatever it is that's on this side, we still have on this side, but it may be in a different order. So things are just being exchanged. Reversible is telling us, well, if the equation goes this way, it can also go this way. It's a reversible equation. And I'm going to give you an example of each of these. And then oxidation reduction. In a previous video, I think we spoke about oil rig. Oxidation is losing, reduction is gaining. What are we losing and what are we gaining? Electrons. If you're losing electrons, that's oxidation. When you're gaining electrons, that's reduction. So let's look at the first one. Let's look at synthesis reactions, which is an anabolic reaction. It's when two or more atoms, ions, or molecules combine to form something new, and that newer thing is going to be larger. It's going to be bigger. So all synthesis reactions in the body, they're called anabolism. And they are endergonic because they absorb more energy than they release. Okay, the formation of water from hydrogen and oxygen molecules is an example. Okay, now this term right here, dehydration synthesis, this is required in synthesis reactions in order to build something bigger from two smaller things. It requires the removal of water. And I'm going to show you what that looks like. And I just want to lay down that dehydration synthesis and hydrolysis are opposite things from one another. They're opposite. And I'm going to show you dehydration synthesis. I'll show you hydrolysis. But when you look at the word, lysis means to split, hydro means water. So that means that you're taking H2O and we're splitting it up. So here's an example of dehydration synthesis. Now on the left side, we see glucose and fructose. Okay, now glucose and fructose, these are forms of carbohydrates. Okay, so is sucrose. Now, when we combine glucose and fructose and bring these two smaller things together, it makes something larger, which is sucrose. That's table sugar. Now, how do these things get brought together? it uses something called dehydration synthesis. So when there is a chemical equation that's drawn out, this is glucose, and you don't have to know the glucose formula, and you don't have to know the fructose formula. But what's interesting is when you look at them, they're the same, right? 6 carbons, 12 hydrogens, and 6 oxygens, C6H12O6. What's fructose? 6 carbon, 12 hydrogen, 6 oxygens. But this is a hexose sugar. This is a pentose sugar. This has 5 sides. This has 6 sides. When we bring these together, look what the body does. Dehydration synthesis. It's pulling water out of this. How? It takes this hydrogen and this hydrogen. What do you get when you bring 2 hydrogens together? And an oxygen. What do you get? You get this on the other side. You get H2O. Okay? So when you bring glucose and fructose together through dehydration synthesis, what that gives us is sucrose plus water. Now, if you wanted to add water to something that you were eating that has sucrose in it, you can go backwards in this direction, except that would be called hydrolysis. Hydrolysis. Because now you got to split the water, put these 2 hydrogens and oxygen back where they belonged, and then you go back to your glucose and fructose. So decomposition reactions, this is catabolism. This is when you take something larger and you break them up and split them into something smaller. All decomposition reactions are catabolic, and these tend to be exergotic since they release more energy than they absorb. And these use hydrolysis reaction. I'll give you an example. So here's AB is going, we take something bigger, AB, and we break it up into something smaller, A plus B. So when you eat meals of protein and fats and carbs, right, which are too complex to be absorbed, decomposition reactions in the digestive tract take place to break the proteins and fats down into smaller molecules. And that's why when you eat a meal, we drink water with it to allow us to metabolize and break down those foods. It's the only liquid we should be drinking, right? There are no Pepsi or Coca-Cola lakes out in the world. There's no Sprite ponds. It's just water, okay? So decomposition involves water to help break it down. We call it hydrolysis. So it's when you take H2O and we break it down into hydrogen and hydroxide. So H is hydrogen. When you have OH, we call that hydroxide. Okay. This is an alkaline. This is alkalinic. And when you add hydrogen to something, it makes it acidic. When a covalent bond is broken, it releases kinetic energy so that we can perform the work. When bonds are being made, it takes energy. When bonds are being broken, it releases energy. That energy is going to be used to perform all the vital functions of the body. So here's an example of 2 monosaccharides, glucose and glucose. It's the same formula, C6H12O6, C612. They're both hexose sugars, 2 glucoses. That's all we're looking at, 2 glucose. They're both monosaccharides. Now we're taking something smaller and we're going to make it something bigger. In the other picture, we saw glucose and fructose and we made sucrose. Now we're bringing two of the same together, two glucoses, and that's going to give us maltose. Maltose, right? Like a malted beer. That's what's in beer. Now, if we take maltose, which is a disaccharide, it's a disaccharide because all we did is we took a mono and a mono to get a di. Two monosaccharides equal a disaccharide. Now we want to go from maltose, which is a disaccharide, and we want to break it down from something larger into something smaller. How do we go from a disaccharide to monosaccharide? Well, this is where we take that water and we hydrolyze it, right? Hydrolysis. Lysis means to split. We're breaking the water. We're going to use this and put it back where it belongs. Here's a hydrogen. Here's a hydrogen, so that's the H2, and there's the O. So when you're pulling water out of it, that's the dehydration synthesis. When you're taking the water and you're putting it back in, that's the hydrolysis. You're splitting it to put it back. Hydrolysis reactions are used for catabolism. Synthesis reactions are used for anabolism. What's an exchange reaction? An exchange reaction is where the substances exchange atoms, meaning it consists of both synthesizing and decomposing at the same time. So on this side, we have HCl, which is hydrochloric acid. And on this side, we have sodium bicarbonate, that's Alka-Seltzer. Okay, hydrochloric acid and Alka-Seltzer. When we combine these together, it gives us carbonic acid and sodium chloride, salt. In an exchange reaction, everything that we have on this side is still on this side, it's just scrambled. Here's the sodium. There's the sodium. Here's the chloride. Here's the chloride. Here's the CO3. Here's the CO3. Here's one hydrogen, two hydrogens, bring them together. There's the H2. H2CO3 plus salt. So everything that's on this side was just brought to this side. We exchanged, we scrambled it, we decomposed to make something else. Okay, this is an acid, hydrochloric acid, sodium chloride. Not sodium chloride, sodium bicarbonate. This is a base. This is an acid. So it brought these two together, and you ended up with carbonic acid and salt, or an electrolyte, sodium chloride. That's a classical exchange reaction. What's on one side is the other side. It just doesn't look the same. It's all scrambled up to create something different. A reversible reaction is as it sounds. It is reversible. The reactants can become the products, or the products can become and revert back to the reactants. So AB can become A plus B, or A plus B can go back to AB. That's a reversible reaction. And we'll see this with what I had just shown you here with HCO3 and H2CO3. So this is important when we're trying to balance out acids and bases. Acids and bases. So when we're trying to balance out the pH, we can use carbonic acid and bicarbonate. So if we take carbonic acid, which is this one, H2CO3, and we add hydroxide to this, so we take something that's an acid and we add OH to it, we get HCO3. If we take bicarbonate, which is HCO3, and we add a hydrogen to that, now you get H2CO3. So bicarbonate whenever you add hydrogen into anything, remember if you have a beaker with water and you're dumping in hydrogens, this becomes acidic. If you add in hydroxide, it becomes alkalinic or basic. So here is the type of reversible reaction. We have carbon dioxide. We breathe in we breathe in oxygen, but our body wants to push out the CO2. So CO2 is in our body. It can react with water, which our body is composed mostly of. So when we have the carbon dioxide reacting with water, we get H2CO3. H2CO3. Here's H2. Here's the C. You have 2 oxygens plus this, and now you have 3. H2CO3, that's carbonic acid. Now, if the body says, hey, we don't want all this acid, then we can remove a hydrogen from that. We can split that and be left with HCO3, which is a bicarbonate. When you remove hydrogens, you become more alkalinic. When you're adding hydrogens, you become more acidic. This has more hydrogens than this. So this becomes alkalinic, this becomes acidic. But this can go backwards. You can take bicarbonate plus hydrogen, add that hydrogen here, and now you go from an alkaline to an acid, H2CO3. Then the H2CO3 can also be broken down into water and the carbon dioxide that we breathe out. So this is a reversible equation. Your body is always utilizing this system to balance out pH, to go from something that's acidic. If it's too much, we become basic. If it's too basic, we can go back to acidic. If there's too much acidity, we can go this way, breathe out the CO2, and you're left with water. Beautiful reversible reactions. And then the oxidation reduction reaction, these reactions transfer electrons between atoms and molecules and are always occur in parallel when one substance is oxidized and reduced. So your oil rig is oxidation is losing electrons, reduction is gaining of electrons. And the classical example of that, this was sodium and this was chloride. Remember, this had 11 and this had 17. So 11 protons, 11 electrons. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 11. So we have to add that additional electron shell, and then there is the 11th. But now in the outer shell, remember, we have something called an octet rule, and the octet rule tells us that the outer shell needs 8 electrons. There's only 1 in that outer shell. When you look at chlorine, the 17 protons, we need 17 electrons. 2 can be in the first shell, right? Remember the formulation is 2n squared, n being the electron layer number 1. So if you put a 1 here, 1 squared is 1, 1 times 2 is 2. 2 could fit in the first. So you got 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 17. We need 7 more. 1, 2, 3, 4, 5, 6, 7, but we need 8. So sodium says, hey, I'll donate one of my electrons here. I will lose one, so I become positive because electrons have a negative charge. I will donate or I will lose an electron. That's oil. Oxidation is losing an electron, which it did, whereas chlorine is gaining the electron. which is the rig, oil rig. Reduction is gaining an electron. That's reduction. Cl minus. So when they come together, Na plus, Cl minus, this one lost an electron, this one gained an electron. This was oil, this was the rig, oil rig. Oxidation is losing an electron, reduction is gaining an electron. Okay, we'll take a break. When we come back, we will start inorganic compounds, and then we'll create another video on organic compounds.